for us to do this. So here's the running example I want in the back of your mind. You work for Big Corp. Okay, maybe their symbol is a lowercase I. Okay, you work for Big Corp. You're on a big high-profile project. Okay, you're eager. They say, hey, if when we finish this project and we sell it, we're going to make so much money that we're going to promote you, give you a bonus and a raise, and oh, by the way, we're going to put you on a deserted island with 5 of your best friends with all the food and drink for the next week. Okay? Got motivation to do it right? Okay? Do you think the malicious scheduler has motivation to trip you up? Right. So now, and this is how I like to think about it. If we have a malicious scheduler, and we have a concurrency bug, we haven't controlled that race condition. If the scheduler wants to be truly malicious, will it just wait until the demo before it messes up? Okay? There are great horror stories in the Intel technology environment, a little community here, about where this has happened. People have said, I ran millions and millions of tests and it always worked. Then I went to a big trade show and I was a featured speaker and I gave this demo in front of not only all my customers, but all my competitors. See where I'm going with this? And it crashed. How many sales do you think we made off that presentation? How many sales do you think we lost? I know someone who worked in one of my groups. I work in a research group. This had happened to him at Comdex, the biggest trade show in the world at that time in Las Vegas. He had somewhere around 800 people in the audience. Brand new technology from Intel. Here's a distributed whiteboard app that also supports distributed conferencing. Oops. Okay. The scheduler, for some reason, knew that during testing was not the right time for that bug to occur. Okay. When it came back, it was like, oh, crap. Looked at his code and he goes, now I know what's going on. It's going to take me a day to fix the code. I just need to go in and put in a bunch of locks. Okay, and we're like, great. But then our vice president came along and said, I'd like to have a meeting with you. Right? He didn't work for our Intel Corporation the next day. Oh. I'm not saying that would happen to you. I'm just saying I know where it has happened. So we would like to avoid that, wouldn't we? We want to take the malicious scheduler out of the equation. And that's what we're going to do. Okay. And once we get a good handle on that, everything we talk about for the rest of the class is going to be in light of concurrency. And if you take the parallel programming class, okay, everything in the parallel programming class is about concurrent programming. Okay. So, we're going to, the basis of what to do when we have 2 threads in the same piece of code at the same time. What we're saying is that they're mutually accessing a shared piece of data. It's the mutual we got to stop. So the general term that's used is we need mutual exclusion. And in order to do that, we're going to need some techniques, and we're going to call those mutual exclusion primitives. Okay? So let's first talk about what is mutual exclusion. And when we think about it, we're like, well, we've been doing this all along in our programming. But it's because we've only had one thread. And when you only have one entity, you automatically exclude all the entities that don't exist, don't you? Okay? But now we're throwing in one or more other entities. And we're always going to think in terms of having at least 2 threads of control. So in order to control this, get this concurrency control, we're going to use mutual exclusion. Mutual exclusion is going to require 2 basic properties. Okay? We're going to have an area where we access the shared data we call the critical section. And we're going to say that only one process or thread of control can be in the critical section at any one time. Okay? Only one thread can be incrementing I at any one time. Okay, that would have solved our problem, right? That was one of our possible orders of execution. And that's got us the answer we wanted. And also, when we do that, we can't have deadlocks. Deadlocks are a particularly interesting thing. Okay? That's where we have a set of processes, or threads of control, that can't make progress until another thread makes progress, but eventually all the threads that have that dependency form a cycle. Okay? And we'll see exactly how that works in a few minutes. Okay? So, deadlock, if we have a process that's trying to get into the critical section, it cannot be blocked from getting into the critical section forever. Because, let me tell you, there's an easy way to have concurrency control. My thread comes along, and it says, oh, I want to access a shared variable. I'll just kill all the other threads. What do you guys think? Is that going to block those other threads from entering the critical section? Is it going to be in forever? Yeah, we're not allowed to do that. Okay, you know, it's like when we go to a buffet. It's like I would be having a really good time if only my little brother had ever been born. Okay, he's embarrassing me. Well, no, you're not allowed to. That's not one of the solutions that is on the table. You can't give them away to gypsies. You can't do any of that kind of stuff. All right. We're just going to have to deal with a little brother or sister. By the way, I'm a little brother. Oh. I speak from experience. So, you know, what's going on here? What's the problem? And how can we guarantee that this problem cannot occur? Okay? So, deadlock. Fortunately, deadlock is mathematically provable. So that means we can say when it cannot occur. We cannot guarantee that it will occur, but we can say when it's possible for it to occur. Because remember that example, different orders of execution could give us the correct result. Okay? And different orders of execution could give us deadlock or not. Okay, so we can talk about when the conditions for deadlock are present and deadlock could occur, and we can talk about when deadlock cannot occur. We're going to go for ensuring that deadlock cannot occur. We have 4 conditions necessary. Oops.
Just to clarify, so the deadlock is when you're blocking a process from being into the critical section
A group of processes is unable to make progress because of a dependency in a critical section. And the dependencies have a couple of features to them. In fact, there's 4, and we're just getting ready to talk about what the 4 pieces are. So there's 4 conditions necessary and sufficient for deadlock. Or if you're a math person, deadlock can occur if and only if the following occurs. Okay? There has never been a time on one of my midterms, and about 80% of the time, I also ask this on the final exam, what are the conditions necessary and sufficient for deadlock? Most of the times I say name and define. So this is something you darn well better memorize for the purposes of this class. All right? This question could be worth as much as 10% of your grade on an exam. That's how important concurrency is. So, strangely enough, the first condition for deadlock is that we have to have a need for mutual exclusion. Well, deadlock is the outcome of doing mutual exclusion wrong. It's kind of like, duh. What we're saying here, though, is that if you're not using concurrency control primitives, you can avoid deadlock. So if you've got a condition where you suddenly go, oh, I need to use a lock, maybe you can restructure your problem so you don't need the lock. Okay? In which case, deadlock can't occur. So one of our programming strategies is to avoid the need for mutual exclusion. We're not going to talk about that in this class. That's an actual concurrent programming. So the parallel programming class, you'll probably look at it. Lots of books out there on advanced thread programming that talk about how to restructure your code to avoid having to use concurrency control. Okay, to avoid the need for mutual exclusion. And usually we restructure the data structure. And so that's kind of a data structures and algorithms question. Our CS350 class does not talk about that, but the graduate algorithms class does. I verified that with the instructors. Now, we're going to have a condition called hold and wait. So, mutual exclusion means that we have a shared piece of data that can only be accessed by one thread of control at a time. Okay? So now, let's say I'm the thread of control that has that resource. Okay? But sometimes I need more than one resource. Hold and wait says I'm allowed to ask for another resource while holding a resource. If you're only allowed to hold only one resource at a time, that is, you have to use it, give it up, and then you can go and get another one, you can't have deadlock. But once I hold it, okay, I hold it, I ask for another resource. The system can't come along and say, because you're asked for another resource, I'm just going to steal that resource away from you. Okay? We say that once you hold it, there's no preemption. It cannot be taken away from you. No preemption is the way that there's a tool called Semaphore that we'll see that what it does is it violates no preemption. But it does it in a way that's safe to your process. It's really quite cool. Then we have to have the circular wait. So I'm holding a resource, and I want a resource, say, from you. But you're holding a resource, and you're waiting for a resource from you. But you're holding a resource, waiting for a resource from you. But you're holding a resource, waiting for a resource for me. We're trying to allocate resources, aren't we? And if we look at this from the standpoint of a graph, this becomes a cyclic graph, doesn't it? So we say no circular wait, and the CS250-51 question, the way to phrase this is there's no cycle in the resource allocation graph. Resource allocation is acyclic, not cyclic. Okay, you guys remember graphs? Talk about cyclic versus acyclic graphs. Okay, the resource allocation graph, if it's acyclic, so I'm waiting on you, you're waiting on him, he's waiting on you, but you're not waiting on anyone. So you'll eventually finish, right? And you will free up the resource and you'll be able to get your resource. You'll eventually finish. You'll be able to give it both those resources. You'll be able to get your resource, eventually finish. I will get my resource and I will eventually finish. Okay? So because there's no cycle on the resource graph, we know that eventually the resources will be allocated. Okay? It might be 10 days. But that's not what we're talking about. Deadlock is forever. And that's what we're trying to avoid. We're not trying to avoid slow. We have no control over that. Okay? So it turns out now that these words and this diagram, okay, you don't even need the diagram. But if I were to say what are the four conditions necessary for sufficient for deadlock, I usually say name and define the four conditions necessary and sufficient for deadlock. There's your answer. Okay? We just need to understand what it means for each of those things. And that's what we're going to be talking about for the rest of the term. And we're going to talk about how to avoid different pieces of them. Because it turns out if all four conditions are present, we could have deadlock, which is kind of sucky. Sometimes it'll run, sometimes it won't. If only 3 of them are present, we can prove it mathematically that we cannot have deadlock. Is there someone over here?
I was just going to say, so then it would be enough to be sure that we won't have at least one of those.
Right. So the general technique is to violate one of those. Okay? So if we go, oh gosh, here's a shared data structure. Well, this is going to be really hard. Almost the first thing we do after we've been programming a long, long time, so you've been in the field doing this for a long time, you go to somebody and they'll say, well, maybe we can use a different data structure in a way that we don't need to have a lock or concur, and we don't have the possibility of deadlock because we violated mutual exclusion. Okay? Or we only allow you to have one at a time. We tell you that no thread can have more than one lock at a time. There's other things that we can do to do this, to avoid, there's several techniques for avoiding circular weight. We're not really going to talk about them. The book, did anybody, when they looked at this in the book, did it mention lock ordering at all? Okay. Oh, the XP6 book does. Okay, so all lock ordering is you're trying to get locks. But locks are just locations in memory, right? Because it just says whether it's locked or unlocked. Right? If you always have to get them in a particular order, and the typical order is the address in memory. Once I get a lock at a particular address, I'm not allowed to get a lock at a lower memory address. I always have to get them from above, or the reverse. And if everybody follows that, it turns out we can't have a circular weight. It's mathematically provable. Okay. But, as it turns out, it's almost impossible to do in a complex program, large complex program. Okay. So it turns out that almost everybody attacks no preemption and mutual exclusion. 1 and 3 are the big things that we go after. But there's very specific applications where it's easy to violate 4, or it's easy to violate 2. Okay, by using very specific algorithms in particular ways, we can do it without having to have 2 pieces of shared data accessible at the exact same time. And we're going to see, it's tricky, we're going to be thinking about it, it's going to be tricky, but we're going to get practice with it.
So even if we hit all 4 conditions, it doesn't necessarily mean we get it.
Yes, these conditions could exist, okay? And if you don't have deadlock, that doesn't mean that you have well-written code. It just means you're lucky. Remember Clint Eastwood? Feel lucky, punk? Okay. All right, remember the malicious scheduler? If these conditions hold, if these conditions exist, it means the malicious scheduler can get you.
So just to clarify completely, if those 4 conditions are met, then it is not possible to
Avoid.
this. It's not possible for deadlock to not be possible.
Okay?
If
I know what you meant. And actually your grammar, your English language is really, really good. That's a really well-constructed sentence. Okay? But I'm going to phrase it differently, which says if all 4 conditions must hold or deadlock cannot occur. Which is what you said, but you said it from the flip side. If these conditions are met, we cannot guarantee that deadlock cannot occur. And the other way of saying that is if even one of these doesn't exist, under no circumstances can we have deadlock.
right.
So, yeah, so what you said was right. Okay, so you had a really good grammar teacher. All right. I was pulling for you because I've messed that up more times than I've ever gotten it right. So that was really good. So now, beginning next time, we're going to say, hey, we have to have specific tools. And we're going to talk about the fact that a programmer cannot provide these tools all by themselves. We require hardware support. Okay? And we're going to talk about it with an idea of a lock, because most of us have seen locks. Has anyone ever been locked out of something? Maybe their house? Okay. You ever done that? You're really careful, your partner or whatever, you just got it set up so the door automatically locks, okay? And you grab your gym bag and you pull it, and it's like click. Do I have my keys? Okay, it used to be really easy to do this with cars. Now my car, the driver's side door, will not lock while the key is inside. Guess how many times that has saved me? I've had the car for 14 years. Let's just say it's a non-trivial number. It has at least 3 digits. So now we're going to talk about lock. The 3 things we're going to talk about in this class are locks, condition variables, and semaphores. And we're just going to build up to them. That's the order we're going to look at. Next time we'll look at locks and condition variables, and then we'll spend an entire lecture on semaphores. And it turns out semaphores are the most general. So locks, okay, how many states does a lock have?
2.
2. Okay, and that's what makes them really easy to understand. It's locked or unlocked.